Swayam Prabha. Digital India. Educated India.
Welcome to the first lesson of third module, which is on thin walled pressure vessels, part 1, which is the application of stress and strain. In fact, in the last two modules, module 1 and module 2, we have looked into the aspects of analysis of stress and analysis of strain. At a point in a stressed body, how do you compute the stresses and strain? Now, we will look into the applications of this stress and strains at a point in a thin walled pressure vessels. In fact, the pressure vessels has wide industrial applications. In fact, in many industries we use this kind of vessels where the pressurized air or water is used. Now, it is necessary to evaluate the strains and the stresses at any point within the on the surface of the pressure vessels, and we will look into how to compute the strains and stresses on the body of such pressure vessels. Now, before we really go into the analysis of the pressure vessels, let us look into the aspects which we discussed in the last module. In fact, the module 2 we had devoted on analysis of strain, and we had 8 lessons in module 2. And let us look into quickly that what were those lessons which we had covered in module 2. Now, the module of analysis of strain includes 8 lessons, as I have told you, and the first lesson was on the concept of normal strain, the strain at a point, and stress strain relationship, and these were discussed in the first lesson. The second lesson was devoted on the aspect of normal strain in a variable section. In the first lesson we had discussed the normal strain in a uniform body. Now, if the body is having a variable section, then what will be the strain in that? Correspondingly, what is the shearing strain, and we had discussed the concept of rigidity modulus in the second lesson. In the third lesson we had introduced the concept of generalized Hooke's law, and thereby the determinate and indeterminate system were discussed. Thermal effects on strains and stresses were discussed in the fourth lesson in L24, module 2 and fourth lesson. Thermal effects on compound bars and the misfit and correspondingly the pre-strain and the pre-stresses was dealt with in the fifth lesson of module 2. In the sixth lesson we had discussed about the transformation equation, and if you remember we had discussed this aspect in the first module of stress as well, wherein we say at a particular point if we are interested to compute the value of stress and thereby the strain, then we need to use the transformation equation if we orient the axis system from reference rectangular axis system, and that is what was discussed in the module in the module 2 lesson 6 L 2.6, where we had introduced the concept of transformation equations and thereby how to evaluate the principal strains were discussed. Then concept of Mohs cycle of strain, how to compute the strain at different orientations at that particular point, where we know the rectangular strain components epsilon x, epsilon y, gamma x y, how to compute the values of principal strain and the strain at that particular point at different orientation. If we like to compute, we can do it through the use of Mohs cycle of strain, and that is what was discussed in lesson 7. And the last lesson, that is the 8th lesson, which we discussed the previous to this, where we had introduced the concept of strain gauge and strain rosettes. Thereby at any point, as I have told you, it is easier to measure the strain and it is difficult to measure the stresses at any point when we talk about a stressed body. Hence, we can measure the strains and thereby from those measured strains we can compute the stresses. But as we have seen, we measure the strains in the normal direction, the normal strain. So, out of 3 strain components, epsilon x, epsilon y and gamma xy, it is very difficult to measure gamma xy, the shearing strain. Hence, we take an indirect way to measure gamma xy by using strain gauges in 3 directions, which we have called as strain rosettes. So, from the measured data of strain rosettes, we can compute the strains epsilon x, epsilon y and gamma xy, and using these strain components we can compute the principal strains and thereby the principal stresses. Well, this is what was discussed in lesson 8 in module 2. Also, we had looked into the relationship between the elastic constants, which were E, G and mu. Well, this was the more or less the summarization of the module 2. Now, let us look into this particular lesson. Now, it is expected that once this particular lesson is completed, one should be able to understand the concept of stress and strain in thin walled cylindrical pressure vessels. Now, here we are concerned with 2 aspects. One is the vessel is subjected to internal pressure, and this internal pressure is over and above the external pressure. By overcoming the external pressure on the vessel, the internal pressure is working, and thereby there will be stresses generated in the vessel, and we are interested to evaluate those stresses. Secondly, this is a thin walled, and this term has a meaning, the thickness of the wall is very small, so that the stress variation across the thickness is significantly small, or we neglect that, and hence the thin walled pressure vessel is of importance, and we will look into that, how to compute the stresses in such vessels, and thereby we will evaluate stresses and deformation in the thin walled cylindrical pressure vessels subjected to internal pressure because of the content in the container. Hence, the scope of this particular lesson includes, well, as we do for all the lessons, we will be looking into aspects of the previous lessons or the recapitulation of the previous lessons, which we will be doing through the question answer sessions. The questions which I have posed for you in the last session, we will look into the answers of those, and thereby we will be scanning through the aspects which we have discussed in the previous lesson. Also, we are going to derive the formulae for evaluating stresses and strains in thin walled cylindrical pressure vessels. In this particular lesson, we will be concentrating on the cylindrical type of pressure vessels, and subsequently we will look into different categories of pressure vessels, and we will look through a few examples for evaluation of stresses, strains and deformations in such pressure vessels. So, these are the 2 main aspects that we will be doing in this particular lesson. Well, let us look into the answers to these questions which I had posed last time. The first question is, how will you evaluate principal stresses at a point from measured strain using a rosette? Now, as I was telling you that when we try to measure stress at a point, we cannot directly measure the stress. Hence, what we try to do is we measure strain at that particular point, and thereby we compute the values of stresses. But the strain components, as we have that epsilon x, epsilon y and gamma xy under a plane strain situation, we cannot measure gamma xy directly. Instead, we measure indirectly, and from there we compute the values of principal strains. Now, let us look into how do we do that. Now, in the previous lesson we had discussed that this is the x direction and this is the y direction. Now, since we can use strain gauges, which can measure the normal strain. This kind of strain gauges, as we have discussed in the last lesson, can measure normal strain. Now, if we place these type of gauges in the x direction and y direction, we can measure the strain epsilon x and epsilon y, but we need three quantities epsilon x, epsilon y and gamma xy for evaluating the principal strains. Since we cannot measure gamma xy directly, what we do is that we place three strain gauges in three different orientations, and let us call this direction as A, this as B, this as C, which we have discussed the last time, and all three are oriented at three different angles. This particular angle is theta A. This angle, the second gauge which is along the B, is at an angle of theta B, and the third gauge which is along C is oriented at an angle of theta C, and thereby employing the transformation equation, which is epsilon x dash is equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta plus gamma xy by 2 sin 2 theta. This is the transformation equation. So, we can employ this equation to evaluate strain along A, along B and along C, which are epsilon A, epsilon B and epsilon C, keeping in mind that epsilon A is acting along A, which is at an orientation with reference to x axis at an angle of theta A. Hence, in place of theta we will substitute theta A. For epsilon B, the orientation is along theta B, and for epsilon C, the orientation is along theta C. So, if we substitute that, we can get equations in this particular form, where we have three equations epsilon A, epsilon B and epsilon C, and they are oriented at an angle of theta A, theta B and theta C. Now, in these three equations, if you look into, we know epsilon A, we know epsilon B, we know epsilon C, and also we know theta A, theta B, theta C, as these are predetermined orientation, the gauges along which it will be placed theta A, theta B, theta C, they are predetermined. Hence, theta A, theta B, theta C are known, and since we are measuring strain along A, B and C, so epsilon A, epsilon B, epsilon C are known. So, in these three equations, then 6 quantities are known. So, only unknown quantities are epsilon x, epsilon y and gamma xy, which we can evaluate from these three equations. Now, once we know epsilon x, epsilon y and gamma xy, now we can compute the values of epsilon 1 and epsilon 1 and epsilon 2. This we have seen we can compute as a function of epsilon x and epsilon y and gamma xy, which is epsilon x plus epsilon y by 2 plus root of epsilon x minus epsilon y by 2 square plus gamma xy by 2 square. So, this is the value of maximum principal strain, and same quantity with minus will give the quantity epsilon 2. So, we can evaluate the value of epsilon 1 and epsilon 2 from epsilon x, epsilon y and gamma xy. Now, if you remember that we had computed the values of strain in terms of stresses, and there epsilon 1 as equals to sigma 1 by E minus mu sigma 2 by E, where sigma 1 and sigma 2 are the principal stresses, epsilon 1 and epsilon 2 are the principal strain, and sigma 1 and sigma 2 are the principal stresses. And as I had told you last time, we had seen that the direction of the principal stress and direction of principal strain coincides. So, we can compute the value of principal strain from the principal stresses in this form, and likewise epsilon 2, the strain in the minimum stress direction, is equals to sigma 2 by E minus mu sigma 1 by E. Now, if we multiply the second of this equation with mu and add up with the first one, we get epsilon 1 plus mu times epsilon 2, which is equals to sigma 1 by E. Now, this is minus mu sigma 2 by E, and this is sigma 2 by E. When it is multiplied with mu, this gets cancelled, So, we have minus mu square sigma 1 by E, or this is equals to 1 minus mu square by E times sigma 1. So, from this we get the value of sigma 1 as equals to E divided by 1 minus mu square into epsilon 1 plus mu epsilon 2. So, this is the value of sigma 1 in terms of epsilon 1 and epsilon 2, and epsilon 1 epsilon 2 we have obtained in terms of epsilon x, epsilon y and gamma x y. So, once we measure strains along 3 directions, we can compute epsilon x, epsilon y, gamma x y, and from those measured values of epsilon x or evaluated values of epsilon x, epsilon y and gamma x y, we can compute epsilon 1 and epsilon 2, and once we know epsilon 1, epsilon 2, we can find out stress sigma 1. Likewise, stress sigma 2 is going to be equals to E by 1 minus mu square into epsilon 2 plus mu epsilon 1. So, these are the values of the principal stresses sigma 1 and sigma 2. So, once we know or once we measure the so we say that how will you evaluate principal stresses at a point from measured strain using rho z, and this is how from the measured strain data we can compute the values of principal stresses which are sigma 1 and sigma 2. Now, let us look into the second questions, that how many elastic constants are necessary for analyzing deformation and how many are independent. Now, we have seen that when we are trying to compute the stresses and the strains, we are requiring 3 constants which are E, G and mu. The modulus of elasticity E, G is the shear modulus and mu is the Poisson's ratio. Now, as we have seen last time, when we were relating the shear modulus with the elastic modulus, out of these 3 constants E, G and mu, which are necessary for analyzing deformation in a stressed body, 2 are independent, and in fact G can be evaluated once we know value of E and mu. So, out of these 3 elastic constants, 2 are independent and 1 is dependent on the other 2. So, this is what is demonstrated here, that G is equals to E divided by 2 into 1 plus mu, and this we have derived last time, and once we know the value of E and mu, we can get the value of G. So, though we need these 3 constants, but 2 are independent. Now, the third question is, can you infer on the maximum value of Poisson's ratio from the expression of bulk modulus. Now, let us look into the expression for the bulk modulus. Now, this particular aspect discussed last time in the last lesson, that dilatation which we have denoted as E is defined as delta V by V, where delta V is the change in the volume and V is the original volume, and that is how it says dilatation is the change in volume per unit volume. If this is equals to 1, E is equals to delta V. Now, in the expression for this change in volume or the dilatation, we have the Poisson's ratio mu. Now, if you look into this, here another term is there which is P. E already you are acquainted with, which is elastic modulus, and P is the term which is hydrostatic pressure which is acting at that particular point in the small element. Now, P is the stress quantity which is acting in all directions in place of sigma x, sigma y and sigma z. These are the values of P, which are called as the state of hydrostatic pressure. That means, that element is subjected to a compressive stress from all sides and it is under the state of a compressive force. So, when if you look into this particular expression where E is equals to minus 3 minus 1 minus twice mu, minus indicates that it is under compression. Now, if we have the value of mu greater than half, then 1 minus 2 mu, this particular quantity, it becomes negative, and once this becomes negative, means minus or minus this becomes positive, which indicates that delta V is increasing, that means the volume is increasing. That means, if the value of mu is greater than half, then it states that there is an increase in the volume, which is contradictory to the physical state. Now, in the physical state, as we see that particular element is subjected to hydrostatic pressure from all directions, thereby sigma x, sigma y, sigma z, they are all P and rather negative P, and this is trying to compress the body. Now, if we have the higher value of mu greater than half, then it shows that it is expanding, which is contradictory to the physical state. So, the maximum value of mu that you can have is half. So, as this we have stated earlier also, the maximum value of mu is equals to 0.5. Well, these are the 3 questions that we had, and in fact, these are the aspects which we had discussed in the previous lesson, and if you go through the previous lesson, you should be in a position to answer these questions. Now, let us look into the aspects which we are going to deal today, and as I have told you that pressure vessel are the containers in which the gas or in liquid is put under pressurized condition, and thereby it exerts pressure in the internal surface of the container, and if that internal pressure is higher than the external pressure, the body will be experiencing stresses, and basically there will be tensile stress in the body. Now, our objective here is to evaluate those stresses in such pressurized containers, and it has quite wide applications in the industry, wherein we use this compressed air, or even water is flowing through a pipe, thin walled pipe, are also kind of examples of these kind of pressure vessels. Now, this is what is stated here, that pressure vessels are the closed structures containing liquid or gas under pressure, and we have qualified these terms pressure vessels with thin walled, and this is very important because the thickness of the wall or the thickness of the container wall is sufficiently small, is so small that the variation of the stress across the thickness is insignificant, and thereby we consider that there is a state of stress which is on the surface in 2 directions. The third direction stress is 0, and we call thin walled those vessels for which the thickness is so small that in comparison to the other dimension, that the ratio R by T, where R is the radius of the cylindrical tank and T is the thickness, if R by T ratio is greater than or equals to 10, then we call those kind of vessels as thin walled vessels. Now, the term 10 or the number 10 here actually is considered that it has been observed if R by T ratio exceeds value of 10, then the error in the stress level is minimum, and that is the limiting value which is considered for considering thin walled vessels. And as I have told you that the internal pressure must exceed the internal pressure, otherwise there will be other kinds of problems, which of course we are not going to discuss at this moment, but internal pressure must exceed the external pressure. Now, also in the pressure vessels, basically when we try to analyze, we try to go for a simplified analysis, and this analysis is based on the effects that the internal pressure exerts pressure or the forces on the body, and thereby the body is subjected to stress, and that is what we try to analyze, that how much stress the body undergoes when the container is subjected to pressure. But we neglect other effects such as effects of the external loads, the weights of content and the weight of the container. These aspects are neglected in this analysis. So, when we try to analyze these kind of pressure vessels, we analyze the container for stresses only because of the pressure which is being exerted by the content from inside. We do not take the weight of the content, we neglect the weight of the container, and we do not take the effect of any external loads that are acting on that particular container. Also, the analysis of such vessels for elastic deformation, when we try to compute the elastic deformation of such containers, this needs the application of generalized Hooke's law. This we have seen that where we compute the strains in terms of stresses in a generalized Hooke's law form, where epsilon x is sigma x by E minus mu times sigma y by E minus mu times sigma z by E, and so on. So, these are the generalized Hooke's laws application, and we take the applications of these for analyzing strains and thereby the deformation in the pressure vessels. Now, we can have different forms of pressure vessels, but in this particular lesson we are concentrating on a pressure vessel which is of cylindrical form. Now, if we have a cylindrical pressure vessel which is exerted by pressure inside which is more than the external pressure, then what will be the state of stress that will be acting on such containers. Now, let us look into one of such configurations, that this is the cylinder. Now, if we cut this cylinder and take a free body, let us say this is a cut AA and BB, these are the two planes by which we are cutting this cylinder. Also, we are cutting this cylinder along this center half, then we get a configuration which is something like this. Now, here this is the thickness, and this thickness of course is sufficiently small, and as we have discussed that this T is such that R by T, where R is the radius of this cylindrical structure, R by T is greater than or equals to 10, and we call this kind of cylindrical form as thin walled cylinder. Now, if we cut, there are forces which will be acting, and mind that there will be internal pressure which will be exerted by the content. Now, if we like to write down the equilibrium, now this configuration can be written down in this form, that this is the half cross section of the cylindrical container, wherein this is the cylindrical part, and this is the thickness of the cylinder, and this is the center. Let us say this is the radius of the cylinder. Now, this is internal radius and this is external radius. So, we can call this as R internal and this as R outer. And the stresses that will be acting, if we take an element on the surface of this cylindrical surface, we have stresses acting in this form, stresses acting in the circumferential direction. Let us call this as sigma 1, and which is acting in the longitudinal direction, let us call that as sigma 2. Now, so in the circumferential direction the stress acting is sigma 1. Now, let us say the resulting force which is acting here is P, this also is P, and the content is exerting pressure on this side. Now, if we try to evaluate the value of stresses, now this P is equals to the stress time area. If we call sigma 1 is the stress which is acting in the circumferential direction. So, sigma 1 times T. Now, if we take the distance between these two cut as say L, which is this length of the segment, which is L, and let us say we are computing stress over this particular length. So, sigma 1 times T times L, T times L is the area, sigma 1 is the stress. So, P is the force that is acting over here. Now, we can compute the values of sigma 1 in two ways. One is, supposing if we take this thin wall part and we say that this is subjected to the pressure from inside, and here we have P, here we have P, which is equals to sigma 1 times T times L. Now, if we consider a small element which is at an angle of theta, making angle d theta here. So, this is theta and this is d theta. Then the force which will be exerted here is equals to the internal pressure P times this is R times d theta, P R d theta, and this is over the length L. Now, if we take the component of this force in the horizontal direction, which is this is theta. So, this is this times cos theta. So, the force which is acting is P R L d theta cos theta, and this is acting over the whole of this segment. So, this side we have P, this side also we have P. So, twice of P is equals to integral. Now, if we integrate from 0 to 90 degree for the two halves. So, 2 of 0 to pi by 2 times P R L cos theta d theta. Now, this gives us a value of cos theta d theta is the sin theta, which is equals to 1. So, this is twice P R L and P is equals to sigma 1 T L. So, in place of P we can substitute this as 2 sigma 1 times T times L. So, this is equals to twice P R L. Now, if we equate these two gets cancelled, L gets cancelled. So, we have sigma 1 is equals to P times R by T. Now, this is called as sigma 1 is called as the circumferential stress, is along the circumference of the cylinder it is acting, or sometimes we call this as hoop stress. So, circumferential stress or the hoop stress is equals to P R by 2 T, hoop stress. So, this stress sigma 1, since it is acting in the along the circumferential direction, we call that as a circumferential stress or hoop stress, which is given as P is the internal pressure, R is the radius of the cylindrical vessel, and T is the thickness of the wall. Now, we can compute this directly as well. Now, we can compute the values of circumferential stress or hoop stress from this particular figure. Now, here again P is equals to the stress times the thickness of the wall multiplied by the length, the segmental length over which we are concentrating. This is equals to P, and since the content is applying the pressure along with the liquid inside. So, this is the projected length over which this force is acting, which is twice R times L. This is the twice R times L multiplied by the internal pressure P. This is equals to twice sigma 1 T times L. Now, if we equate these two, from this we get the value of sigma 1 as equals to P R by T. So, we can see that the value of the circumferential stress in a pressurized cylindrical vessel is equals to P R by twice T, P R by T, where sigma 1 is called as the circumferential stress or hoop stress. This is called as circumferential stress or hoop stress. Now, one point must be noted here, that I am using the value as R, though initially I had stated two values of R, one is R internal, another one is R outer or the external. Now, since the thickness of the vessel is very small, we consider that there is little variation between the radius, internal radius and the external radius, and we consider the radius as internal radius and compute stresses for all, as we have assumed in the beginning that since the thickness is small, the variation of stress across the thickness is negligibly small, and hence we consider only one R, which is the internal radius R, and that is why I am writing always this as R. Now, if we like to compute the value of the other stress, which is sigma 2, which is acting in the longitudinal direction. Now, to do that, particular aspect, let us take the section here, which is shown in this particular figure. Now, here you see that we have internal pressure which is acting on this particular surface, and the thin wall which is subjected to the forces in this form, which is resisting this internal one. Now, let us write in terms of internal and external radius over here. This is internal radius and this is external radius. Now, the pressure which is exerted by the content inside the pressure vessel is equals to the area, which is pi r internal square multiplied by the intensity of the pressure. So, capital P, we can write this as pressure P multiplied by pi r internal square. Now, on the outer periphery, on the thin wall, which is between r internal and r external, this is subjected to a force which is resisting this pressure from within. Now, if we write down that, let us call that as P dash, which is equals to stress we have said as sigma 2. Now, sigma 2 multiplied by the area will give us the force, and the area is pi r outer square minus r pi r internal square. So, from the whole of the cylindrical surface with external radius r outer, if we subtract the internal part with radius r internal, so the force that will be given by the walls is equals to pi r outer square minus pi r internal square multiplied by the stress. So, that is the force that is going to resist this internal pressure exerted by the content. Now, if we equate these two, we can write P pi r internal square is equals to sigma 2 times pi. Now, r outer square minus r internal square, we can write this as r 0 minus r I, or r outer minus r inner into r outer plus r inner. Now, r outer minus r inner basically gives the thing, r outer is this and r inner is this. The difference between these two is nothing but the thickness. So, this we can replace as T. So, this is equals to sigma 2 pi times T. Now, here you see we have two quantities, r outer and r inner. Now, since the thickness is very small, and as I am telling you constantly that there is little variation between r internal and r outer, because the thickness is significantly small. Hence, we consider r outer equals to r inner equals to r. So, if we do that, then this is basically twice r, and we have on the left hand side r I square, which is also r. So, we have now from this pi gets cancelled, r square and r gets cancelled. So, we have sigma 2 as equals to P r by twice T. So, you see now here we have obtained the expression for the longitudinal stress, which is sigma 2, which is equals to P r by twice T. Now, earlier we have seen that we have the circumferential stress or the hoop stress sigma 1 as equals to P r by T, and now we have obtained the longitudinal stress, which is sigma 2, which is in fact half of this circumferential stress, which is P r by twice T. So, if we know the internal pressure, if we know the radius of the cylindrical vessel, if we know the thickness of the wall, we can compute the stresses, the circumferential stress and the longitudinal stress. And both the stresses, the sigma 1 and sigma 2, the circumferential stress or the hoop stress and the longitudinal stress, they are basically tensile in nature. Well, having looked into the concept of the stresses in the cylindrical vessel, let us look into some of the problems. Now, let me discuss the problems which I had posed last time, which were with reference to the stress system or with reference to the Mohr circle of strain and the transformation equation, and then subsequently we will go to the examples of the pressure vessels. Now, the first example which I am discussing, in fact this I had given you last time, and I am sure by this time you could solve this. Just for your reference, you can check that whether your solution is correct or wrong. What I had stated was that an element of material in a plane strain condition is subjected to epsilon x so much, epsilon y is 70 into 10 to the power minus 6 and gamma xy as 420 into 10 to the power minus 6. What you will have to do is evaluate the strains for an element which is oriented at an angle of 75 degree with x axis in anti-clockwise direction, and secondly the principal strains, and thirdly the maximum shear strain using Mohr circle. Now, let us look into quickly that how do you compute these values of the principal strains, the maximum shear strains and the strains which are at an orientation which is oriented at an angle of 75 degree with reference to the x axis. Now, let me draw the Mohr circle corresponding to the state of stress which is given. Epsilon x given is equals to 480 into 10 to the power minus 6, epsilon y is given as 70 into 10 to the power minus 6 and gamma xy is given as 420 into 10 to the power minus 6. Now, if we try to plot the Mohr circle based on these values of strains, then we have, let us say this is our epsilon axis and this is positive gamma xy by 2 or gamma by 2 axis. Now, here we have the point which is the positive epsilon x and gamma xy by 2, and correspondingly we have epsilon y and gamma xy by 2. Now, if we join these 2 points together, the line which crosses the epsilon point, we get the this as the center of the Mohr circle, and this if we call as O, O A dash or O A, if we take this as the radius, then we can compute or we can draw the Mohr circle in this form. Now, here in this particular point indicates the value of the maximum strain, which is the principal strain, which is equals to epsilon 1. This strain is the minimum normal strain, which we call as epsilon 2, and as we have seen, the distance of the center from the origin is equals to epsilon x plus epsilon y by 2, and the distance between these 2 points A dash, as we have seen earlier, this is epsilon x minus epsilon y by 2. Now, if we designate them, let us say this is B, this is B dash, and let us call this as O dash, and this as say x and this is y. So, the distance O dash is epsilon x plus epsilon y by 2, which is equals to 480 plus 70 550 by 2, and this is equals to gives us 275. The value of this is equals to 275 into 10 to the power minus 6, epsilon x minus epsilon y, which is 410 by 2, that means this is 205 into 10 to the power minus 6. Now, this distance is epsilon x minus epsilon y by 2. This is of course epsilon x minus epsilon y, and from here to here this is epsilon x minus epsilon y by 2, and this distance is gamma xy by 2, which is 210 into 10 to the power minus 6. Thereby, from this particular triangular configuration, this is 210 and this is 205, and this is the radius of the circle, which is OA. OA is equals to radius r, which is equals to root of 210 into 10 to the power minus 6 square plus 205 into 10 to the power minus 6 square, and this gives us a value of 293.5 into 10 to the power minus 6. Hence, let me first compute the principal strength epsilon 1. Epsilon 1 is equals to O dash or O dash O plus the radius. So, O dash O plus R, and O dash O, which is equals to epsilon x plus epsilon y by 2, which is 275. So, 275 plus 293.5 into 10 to the power minus 6 is the strain, and this gives us a value of 568.5 into 10 to the power minus 6. Now, epsilon 2, which is the minimum principal strain or minimum normal strain, is given by this distance, and that is equals to again the radius minus or O dash O minus radius, eventually that will become negative. Now, O dash O is 275 and minus 293.5 into 10 to the power minus 6, that gives us a negative value. That is why the end of the circle has gone beyond the 0 point, and this is equals to minus 18.5 into 10 to the power minus 6. So, this is the maximum principal strain and this is the minimum normal strain or the principal strain. Now, maximum shearing strain is the maximum value of the radius, which is equals to gamma by 2, and radius as we have seen is 293.5. So, gamma max is equals to twice of the R, which is equals to 7587 into 10 to the power minus 6. This is the maximum value of the shearing strain. So, these are the three quantities: maximum value of the principal strains epsilon 1, epsilon 2, and gamma max is this. Now, let us look into the angle. Now, since this is the point of the maximum strain, principal strain, now the angle from the reference point is this, which is 2 theta p. Now, this angle is 2 theta p. Now, let us see the what is the value of two theta p. Now, tan of 2 theta p is equals to this divided by this, which is 210 divided by 205, and thereby theta p 2 theta p comes as equals to 45.7 degree, and theta p thereby comes as 22.35 degree or 85 degree, 22.85 degree. So, this is the orientation along which the principal strain acts. Now, what we need to do as per the stated problem, that we will have to compute the value of strain with reference to axis. Now, we have reference axis x and y. Now, we will have to find out the state of strain at an orientation of the axis, which is 75 degree in an anticlockwise form with reference to x. So, we will have to find out the strain along x1 and y1. Now, when we take 75 degree in the reference plane, in the Morse plane, that becomes 2 theta, which is 150 degree. Now, from this particular reference point, if we go 150 degree, now we come somewhere here. So, this is the point which will give us the state of stress, which is oriented at an angle of 75 degree with reference to x axis. Now, from here to here, this is 150, 2 theta p we have obtained as 45.7, this is 90. So, this angle, if we call this as alpha, then alpha is equals to 150 minus 45.7 minus 90. So, this gives us an angle of 14.3 degree. So, alpha is 14.3. Now, from here if we drop a perpendicular, so this distance is going to give us the value of the normal strain, which we call as epsilon say 75, and if we take diametrically opposite this point, we will get epsilon y, and this value will give us the value of gamma by 2. So, let us compute then. Now, if we know that this angle is 14.3 degree and this is radius, then we can compute this distance, let us call this distance a, and the vertical distance which is, let us call this as b. So, r cos theta will give us, or cos 14.3 will give us b, or sin 14.3 will give us a. Now, let us calculate the value of a and b. So, a is equals to r of sin 14.3, which is 293.5 into 10 to the power minus 6 into sin of 14.3 degree, which is equals to 72.5 into 10 to the power minus 6, and the distance b, vertical distance b, which is equals to 293.5 into 10 to the power minus 6 into cos of 14.3 degree. Now, this is equals to 284.4 into 10 to the power minus 6. So, once we know a and b, then the epsilon x on that particular, epsilon x 1 is equals to the distance o dash minus a. Now, distance o dash is 275 minus 72.5 will give us the value of epsilon x 1, and epsilon y 1 will be likewise 275 plus 72.5 into 10 to the power minus 6, and gamma x y by 2, gamma rather x 1 y 1 by 2 is equals to the distance b, which is 284.4, and thereby gamma x 1 y 1 is equals to 568.8 into 10 to the power minus 6. So, these are the values of the strain epsilon x 1, epsilon 1, epsilon y 1 and gamma x 1 y 1 with reference to axis which is oriented at an angle of 75 degree with reference to the reference x and y plane. So, those are the values of the strains and the principal strains and the maximum shearing strength. We have seen how to compute it. Now, this is the orientation or the final form of the reference plane if this is the x direction and this is the y direction. Now, when we have the orientation for the principal plane, which is theta p is 14.3 degree. So, this is the direction along which the principal strain acts. So, this is epsilon 1 and in this direction we have epsilon 2. Now, epsilon 2 was negative and that is why it is compressed and this is elongated. So, this is the form of the principal strain. Now, let us look into the second problem, which was stated as that the strain epsilon x is 120 into 10 to the power minus 6, epsilon y is minus 450 into 10 to the power minus 6, gamma x y also is negative 360 into 10 to the power minus 6. You will have to find out the principal strains and the maximum shear strain using Mohr circle of strain. Now, if we plot the values of the Mohr circle, or if we plot the Mohr circle based on the values given here. Now, here note that we have the values of epsilon x as equals to 120 into 10 to the power minus 6. We have epsilon y which is equals to minus 450 into 10 to the power minus 6, and we have gamma x y which is equals to minus 360 into 10 to the power minus 6. Now, if we plot this, that epsilon x is 120 and gamma x y is minus 180. Now, again this is positive epsilon axis, this is positive gamma by 2 axis. So, we have this as 120 and this as 180. So, this is 180 because gamma by 2 and this distance is equals to 120, which is epsilon x, and likewise we have this point which is epsilon y which is equals to 450 and this is equals to 180. Now, with this if we join them and plot the circle, this will give us the value of, this is going to give us the epsilon 1 and this is epsilon 2. So, we can compute the value of principal strain, because radius equals to root of this square plus this square, and the principal strain is equals to the distance from center to this plus the radius, which will give us the value of epsilon 1 and epsilon 2, and epsilon 1 comes out to be 172 into 10 to the power minus 6, and epsilon 2, which is negative, comes out to be as minus 502 into 10 to the power minus 6, and gamma max, the shearing strain, comes as 570 or 674 into 10 to the power minus 6. Now, let us look into the third problem, in fact, which is related to the example which we have discussed today. Now, here the cylindrical steel pressure vessel is subjected to an internal pressure of 1 megapascal, and the radius of the cylinder is 1500 millimeter, and thickness of wall is 10 millimeter. We will have to determine the hoop stress, which is circumferential stress, and the longitudinal stresses in the cylindrical wall. Now, also we will have to calculate the change in diameter of the cylinder, which is caused by this internal pressure. Now, let us look into the values of the stresses as we compute. Now, as we have seen that the circumferential stress sigma 1 is equals to P r by T, and the longitudinal stress sigma 2 is equals to P r by twice T. Now, here P is given as 1 MPa, R is given as 1500 millimeter, and T is 10 millimeter. Hence, sigma 1, the circumferential stress or the hoop stress, is equals to 1 times 1500 divided by 10, which is equals to 150 MPa, and thereby sigma 2, the longitudinal stress, is equals to P r by 2 T, which is nothing but equals to sigma 1 by 2 is equals to 750 MPa. Now, as we have seen that sigma 2 acts in the longitudinal direction of the vessel, which is longitudinal stress, and sigma 1 acts in the circumferential direction. Now, if we like to find out the increase in the diameter, that means we must know how much strain it is undergoing in the circumferential direction. So, we are interested to evaluate the strain in the circumferential direction, which we call as epsilon 1. Now, epsilon 1 thereby is equals to sigma 1 by E minus mu times sigma 2 by E. Now, if we substitute the values of sigma 1 and sigma 2, we will find that the value of strain which we are getting from here is equals to 0.6375 into 10 to the power minus 3. So, this is the value of the strain which it is undergoing. Now, this strain in the circumferential direction we can write as is equals to twice pi to r plus delta minus twice pi r by twice pi r. So, this is the extension by the original length, which is equals to delta by r. So, the extension in the radius is equals to epsilon times r, which is equals to 0.6375 millimeter. Hence, the increase in the diameter which is twice delta is equals to 2 into 0.6375 millimeter. So, this this r is equals to 6375 multiplied by 1500, and this is 637 times and 1500. So, this comes out as 1.912 millimeter. Well, I have another problem which is set for you, which is an aluminum wire is stretched taut across the diameter of steel cylindrical pressure vessel. The diameter of the vessel is 2000 millimeter and thickness is 10 millimeter. If the vessel is pressurized to 1 megapascal and at the same time the temperature drops to 50 degree centigrade, what stress do you expect in the thin walled pressure vessel? I will discuss this problem next time. Well, to summarize then, that we have discussed the concept of stresses and strain in thin walled cylindrical pressure vessels, and thereby we have discussed hoop stress and longitudinal stresses, evaluation of deformation using generalized Hooke's law, and examples to evaluate stresses, strain and deformation in thin walled cylindrical pressure vessels. And the question set for you are, what is hoop stress and how is it related to longitudinal stress in cylindrical pressure vessels? What is the value of in plane shear stress, and are the stresses same in spherical vessels as well as we see in cylindrical vessels? Well, thank you very much for your attention.